So welcome to this pre-recording of the third lecture of MCS 320, Introduction to Symbolic Computation. So this is the beginning of our second session in the summer of 2022, and in a way we are rebooting. We are getting started, getting help, and with the slides I would like to introduce also the concepts of precision and accuracy. So there will be a short slide presentation, 4 slides to be precise, with some of the essential points, somehow the summary of this lecture, and then I will switch to a Jupyter notebook. Okay, what are the essential points in this course? So we are using Blackboard for online lectures that happen during the prescribed times, but most information is available at the course website listed here. We are using the free open source system SageMath, and the main action item for this week is to install it on your computer, so for which you will be using the org website. So there are binary installers that you can find on the GitHub links. Alternatively, or perhaps in addition, it might also be good to sign up for the cloud service available at Cocalc. So that's the second essential point. So there are many resources available, but actually the most important resource for this course will actually be the Jupyter notebooks that you will make. So there are a lot of reference material, but when it comes to the exam, the most valuable resources should be the exercises and the problems that you have solved during the course. Okay, so getting help. So there is help from me. So I have office hours scheduled 3 times a week. This is an online course. We meet online. If the scheduled office hours do not work for you, then we can make an appointment. There is a TA grader for this course, and there are office hours as well. So the TA grader is responsible for quizzes and homeworks. So if you need help with homeworks, please contact the TA grader. As we will see in the second part of this session, I will illustrate how to get online help. SageMath is very well documented and might be a little bit overwhelming at first. Then there is, of course, always the reflex to start using search engines. So search engines are very valuable as well. Of course, be aware that you may get into rather specialized topics then. So sometimes, I also learn a lot from search engine that brings me to the developers pages, to issues that were resolved, and sometimes these resources are very useful to get a feeling of the question that you're asking, is there a solution for or not. It's not such a good way to make the quizzes and the exams. Then actually I expect that you will have some ready knowledge available. Okay, getting started, getting help. Now let's get into the way how we can compute with SageMath. It's very important that we understand the difference between precision and accuracy. And before we can do that, we need a definition. So the precision of a number system is the smallest number you can add, or we can add, to 1 and still make a difference. That seems rather an artificial concept, but it's related to the way we compute inside a number system, and it can be verified rather directly. Here you see an example. Suppose we have a decimal number system. In the symbolic world, we prefer to think decimal because we have 10 fingers, and also because that's the most natural way to think about numbers. Some computer scientists may, of course, disagree, but I give also an example of the binary number system. So if you have only 3 decimal places to work with, and you have one here, 1.00, and you want to add 1 over 1000 to it, then you see that you would like to represent this as 1.001. So just adding means just adding that 1 to here, but you only have 3 decimal places in your number system. So that added 1, which is just now here adding the symbol, so the plus is not really an arithmetical operation per se. So we add a 1, but we can't represent the exact result in our 3 decimal number system. So the 1 plus 0.01 is actually too small for this. So it's the smallest number that we can add and still make a difference. So we have to pick a larger number that we can add and still make a difference. Now I see, to my embarrassment, that actually the smallest is wrong. It should be the largest number that you can, smallest number that you can add. So here, if we tried to add the 1 over 1000, if we change this to 5 over 1000, then you see that with the rounding, it becomes 1.01. So the machine precision is then the largest, smallest number that you can add to the 1 and still make a difference. In numerical analysis course, we will go very carefully over the internal representation of floating point numbers. Here, with this example, I want to indicate that we can do exactly the same, but then there's still a lot of typos on this slide, I'm sorry. So the 0 here should be cut off. So 1 over 1000 is, no, I'm sorry. So it's okay because we have only 1 and zeros. So even if we would round up here, we would still end up with 1.001. But here, if we round, then we have the 1.01. So it's not the same number. So this is the number represented in binary, and 0.001 is 1 over 8. So what is common in these two representations is the 3, or the negative 3. And what is common here is the 3 as the number of decimal places, or the number of bits that we have available. Okay, so then what is accuracy? Accuracy is a property of an approximation. It's the relative error. But then what is the relative error? So we compute the relative error as the absolute value of the difference between the exact number and the approximation. That's the absolute error, that difference, but we want to know the relative error, so we divide by the exact value, which should actually not be 0. Okay, so here is a question. What is now the accuracy of 22 out of 7 as an approximation for pi? Well, here you see it. Here you see the definition. And this is the symbolic definition. The slides are, in a way, the concepts at least, are independent of a specific computer algebra system. So this is the symbolic representation for this relative error, which we will compute when I switch to the Jupyter notebook. Two important points on the difference between accuracy and precision. So do not misuse these words, do not use one for the other. It's not because we are computing with, say, 32 decimal places that everything is accurate with 32 decimal places. As a matter of fact, the accuracy depends on an approximation, and here the approximation 22 out of 7 over 7 is actually a perfectly exact rational number. It is within the context of approximation that this number actually has a limited accuracy. Our precision, by the way, is always limited. But with computer algebra, we can work under the illusion that we can work with arbitrary precision. The second important thing is, and we touched on that last time already, is that if you really want to know what is the error, then you should be computing at a precision that is at least as high as the accuracy of the approximation. So in that sense, they are of course related. You cannot expect in general, of course, if you're but I'm using pi and transcendental number, but in general, one should not expect to have a higher accuracy than the size of the precision. Okay, so this was the first part of this lecture. Let me now move over to the experimental part where we are computing. So here you see the result, the prepared worksheet, the prepared notebook. So the default interface with Sage is now a Jupyter notebook. It used to be Sage worksheet, so that's why I misspoke. So in the second part of our last session, or in lecture 2, we indicated the main capabilities of a Jupyter notebook. We can document our computations and also give structure. So the theme of this lecture is getting started, getting help. So we will use this example here as a starting point. So let me start from scratch. So in my internet at home did not allow me to connect to CoCalc. But if you start up, if you have installed Sage, you have to make a Jupyter notebook. The first critical decision is actually to select a kernel. It's also very good if you somehow structure your file system good. So here I have navigated when the Jupyter notebook came up. I have navigated to the particular folder where I want to place my Jupyter notebooks. Okay, I will start from scratch. So in the CoCalc environment, you will have to select first a project, and then within the project you have to launch a Jupyter notebook. So Sage, the CoCalc environment is very extensive, so there are many choices there. You first must choose the Jupyter notebook. So that is our default interface, and then the kernel. So you can verify this here that I work with SageMath 9.3. Why 9.3? Because that had a binary installer for Windows. So I did not install the latest version 9.6. But I do have on another laptop also 9.6, and we can also use the cloud. Okay, what is the other thing that you do before you do anything? You change the name. So I will change the name, rename this as MCS 320 Lecture 3 recording. So that is the notebook that I'm using during my recording. There will be a notebook posted at the at the course website. So that is the course website, that is the notebook that I'm using to prepare for the lecture. So there are many variations, there are many versions, but again, the most important resource is actually the notebook that you will be making for this lecture. So it's very important that you do the computations. Okay, so in this lecture 3, we use SageMath as a calculator, and we explore the help, and look at the arbitrary precision floating point arithmetic. So that's how kind of the summary, the one-line summary, what we are going to do in this lecture. Let me make a header. So getting started. So we are getting started now. So what we want to compute, we want to verify the accuracy, or compute the accuracy of 22/7 as an approximation for pi. So I can, with restructured text, I can indicate that 22/7 is something special. So that's something that I will compute. So that is our rational number approximation for pi. The $$ and the /pi is the formatting, the LaTeX formatting to be precise, for the mathematical constant pi. So the reason that we are doing this, so I have to change this into a markdown cell, the Greek letter pi indicates for the mathematical transcendental constant pi. Okay, what is it again that we're trying to do? We are computing the relative error. So I will type in the formula, the relative error, which is the, clicked too soon. So an invalid syntax, of course, I wasn't finished yet. So I take the absolute value. So this is using Sage as a calculator. Note that the fraction will be coming. Note that Sage knows pi, so I can use pi. So let's see if I have syntax errors. No, I don't have syntax errors. So we can print, but there is the pretty print, or the show feature. So here you see the symbolic result. If I do type error, I couldn't resist this. So if I do, everything is typed and object oriented. So you see that I just defined a symbolic expression. If you are asking what is the relative error for 22/7 as an approximation for pi? Well, here it is. So this is the symbolic answer. So we have the symbolic answer, but that doesn't answer our question. So our problem is to compute the accuracy. So that is what is the actual error? I will emphasize numerical error of 22/7 as an approximation for pi. Okay, so we need to compute a numerical value, and how do we do this? We apply the n operator, and then we have to select the digits. Very important here, we have to do a computation, a numerical computation, and that accuracy should be at least as high as the expected accuracy. So we can play with this a bit. You could say, look, I'm going to use 2. So, and then actually with 2 decimal places, I get 0.00. So that means that if I would compute with 2 decimal places in a number system with 2 decimal places, 22/7 is indistinguishable from pi. So one may not conclude that the accuracy of 22/7 is 0. So one can play with this a little bit. So you can eventually you can even do this in a list comprehension. So here you see that I need at least 3 decimal places. Okay, so when we compute this error, so let me describe this, let me document this. When we compute the error, or the numerical value of the error, we must select a precision at least as high as the accuracy of the approximation. Okay, so it shows that we have 3 decimal places. We can do this a little bit. So at 3 decimal places, 22/7 is separate, is distinct from pi. We can verify this too with the scientific notation. So let's do some Python formatting. So what I can do is I can use this percent operator. So I have my formatting symbol, and then I can write 00355. So in scientific notation, we read the numbers from right to left, and you can see that the error is 4 decimal places, or if you want to be a little bit more secure, you can do 3 decimal places. You can also use the negative of the 10 log, so you can effectively also compute this. So another way, and I will need the 10 log later, we can also take the 10 logarithm of the error to compute the number of correct decimal places. So I have the error, so I can do log error, and I will take the 10 logarithm. So here you see that I get to the 3 decimal places as well. If you like, one can do the absolute value. Now it depends whether you are rounding or taking the ceiling. So one can look at the decimal at the scientific notation and notice the 4. So if you answer, so in this course, it's important that you can justify. You can say 3 decimal places correct if you look at the error computation, if you look at the absolute of the logarithm, but you can also say, look, there are almost 4 decimal places correct if I look at the scientific notation, because the error is of the order 10 to the power minus 4. So of the order being that what is most important here is what comes after as the exponent in the scientific notation. Okay, just to make clear here, so I should probably document this as well. So in scientific notation, the 6e minus 0.4 equals, in LaTeX, 3.6 times 10 to the power minus 4. So sometimes people confuse the e for the transcendental constant e, and that's very unfortunate. Okay, I have to speed up a little bit. Well, no, I still have 20 minutes time. So let me go over to the second part. So we got started. We were using SageMath as a calculator, getting help. There is the help from Python as well. I can do help n. So I'm using the dot n. So here I use the error dot n. What is this n now? Okay, so what do I see when I do help n? I see that the n is actually an alias or another name for the method numerical underscore approx. And what I need to highlight here is that why do we always verify things? Well, notice that no guarantee is made about the accuracy of the result. So one gives a warning. So we are doing numerical approximation in a computer algebra system where we are geared towards essentially symbolic, and there's also exact computations. Okay, so suppose that, so I was knowing what I'm doing here, so we see that the numerical approximation is another, and you will see this, so I can do numerical approx and I get the same. So, and here is how you will do this. Now suppose now that you do not know, and there's something else that I will need to point at. So we have the number of digits and there is the precision. The precision is expressed in bits, which is natural from the perspective of a computer where everything is binary. It's probably not so natural for us with our 10 fingers. So in this course we actually prefer the digits. Now suppose now this is about getting help. Suppose that we didn't know a numerical approximation. So suppose, so help is very good because it gives you, so this course follows computer literacy. So if you have taken a Python class, then you must be familiar with the concepts. If not, then this gives you also a feeling on how to learn more about specific commands. But suppose now we did not know neither the n nor the numerical underscore approx. So the help is very useful if you know what is the command that you are going to use. And to be honest, most of the time you may not know it. But here is what we can do. We can do search the entire documentation for numerical approximation. So let's try that. The documentation is very extensive, and here you see that what comes up is a very long list of topics. So again, it's very useful to do this sometimes. It's another way to learn, to explore Sage. I want to indicate the structure of the documentation. So there are constructions. Constructions are mainly here geared how do you do things. And in some sense, this is already a very useful link. So it's related to calculus. And the first two links actually are constructions and also preps, which are geared towards tutorials for undergraduates. And then you see all the references. So any documentation has a getting started, a tutorial, a user manual, and a reference manual. So if you like, we have the tutorials. So there are tutorials as well if I scroll down. So here you see the tutorials without the tours. So I hope that at the end of lecture 1, at the end of our first session, you actually did a tour of Sage, and this homework problem will be collected and you will get credit for this. So please explore as much as you like. So there are tutorials, but then what I was saying, there is the reference manual. So the reference manual is very good for the developers. So this is where the developers spell out in great detail where the numerical approximations come in. And you see also a strength of Sage is in computational number theory. So the word numerical approximation should be treated in more the broader sense. So I was using this for a floating point approximation, but also 22/7 is a rational approximation. So it's also a numerical approximation for something that is a symbol. Okay, I can see everything now in a Jupyter pager. I will not explore here, but you can see that there are many ways where numerical approximation occurs. And the documentation keeps on growing. Okay, that is one way how to get help. Again, if you are in a quiz or an exam situation, please do not do this, or this should really be the last resort. It's good to explore on your own time, and if you do have time, but it's not so good to do the help and the search documentation all the time when you are really need to solve a problem with what you know already. Okay, so my last section that I prepared is on arbitrary precision, floating point numerical arithmetic. So arbitrary precision floating point arithmetic. Long word. So floating point arithmetic is often synonymous with machine arithmetic. So floating point arithmetic is often synonymous with machine arithmetic. And computers are still optimized for floating point arithmetic. In computer algebra, we can compute with any precision we like. So the real field is, we are with the help now. So the real field is a construction that allows you to define a specific arbitrary precision floating point number system. So you can call it without any arguments. So if you can read Python, then you see that what the defaults are. So 53 is the default double precision, 53 bits. You can indicate whether you want to see all your numbers with scientific notation. It's kind of perhaps the default should be 1 and not 0. So perhaps you may want to see all your floating point numbers with scientific notation, as we do in numerical analysis. Okay, very nice and neat. Now you can also ask for random numbers. So the third argument gives you, if you're out of inspiration and you need some numbers, so you can generate random numbers from your field. We may use that feature later. Okay, so what I want actually to say is that there is no digits. There is no digits keyword. So you have to specify your precision with bits. So that's kind of so there's a lot of documentation there. Let me write that down. Suppose we want to define a real field with 8 decimal places of accuracy. Then we must compute the number of bits that are required for this precision. And you see what happened, right? I mangled up accuracy with precision. So thinking I want all my computations to reach an accuracy of 8 decimal places, but actually the only thing I can ask for is that all the computations are done with a precision that could give me at most an accuracy of 8 decimal places. Okay, so how do we do this? Well, I mentioned the logarithm. So I can compute, I will take the ceiling, that the ceiling is the largest integer number. So, and I need to know how many bits I need for 10. So P gives me the precision, and I can compute then the real field where I set the precision to P. So what can I do? I can do the show of R8. So it gives me not really what I wanted. It gives me the pretty print. So let me print what is R8. And perhaps also print R8, and I should probably also print out P. Okay, so if I want there is something wrong with this here. I want 8 decimal places. If I want 8 decimal places, then um, I need to take the 2 logarithm, not the 3 logarithm. Here we are. So if we want 8 decimal places of accuracy, then I need at about 27 bits. So here you see where the impreciseness of our 10 fingers comes in. There is actually not really one specific precision with bits that will exactly match the 10 decimal places. If you really want this, then you have to compute with decimal arithmetic. So here I'm kind of getting at the right precision. What can I do with this now? Well, here you see I can now take pi, the pi in the sky, which is a symbol, a transcendental number, and I can kind of project it down into this field. And here you see the approximation. So let me immediately verify this, if this is now really with 8 decimal places. So you see kind of it is. If I would round the 7 up, then I will get the 3. Okay, so I'm about 40 minutes in. In preparation for the real lecture, I should probably not go any much further here. What I still want to illustrate is the feature that now I have erred a little bit. I made some mistakes. And what I still want to illustrate is that you can restart your kernel and clear all the outputs. So in a way, when you are going to make your Jupyter notebooks, which will be your resources, so here I'm writing everything down in my words. It's also very important that you can say things in your own words. So if you want somewhere a clean version of this, then you restart the kernel and then you run everything. If you want intentionally mistakes in there, then that will fail. It will get stuck. But here you see the operations that are happening. So it actually did execute everything. So you see I have 12 statements that I ran. So in this course, it's important that we know what are the important commands, but we are not doing that many computations. And actually, sometimes less is more. What is important is that one can explain, justify, and most importantly, understand what it is that we are really doing. Okay, there are unsaved changes, so Sage checkpoints, but it's always good to actually often especially click on the save button. Okay, with this lecture is somehow a reboot of our first lecture, but now properly being done with the Jupyter notebook. You can see that I have 3 sections and not that many statements. It could have been with less. When I prepared this, I actually did have less statements, but documented. What is the problem? What is the question? What is happening in each stage? Okay, thank you for your interest in this lecture. With this, I conclude.